Okay, that's all I wanted.
Yep.
I want to just take a minute here to kind of launch this, well, I don't know if I should call it morning, afternoon, or whatever proceedings, depends on where you are. Welcome. This is Aditya's thesis defense. These events are always much nicer and more enjoyable when we can gather in person and just get together. But I think everybody will appreciate that Zoom's kind of the best thing that we've got. It's really our only option these days, and it works. Actually, one feature of these Zoom meetings is it doesn't make it better, but it's a feature. It makes it possible for folks around the world to participate a whole lot more conveniently. We actually, I think, have people from, I know we have some folks in Australia, maybe what, UK, I don't know, but we've got some folks from around the world visiting today, so that's great. Let's see, I suspect that everybody here, most everybody knows Aditya. Real quick introduction, he did his bachelor's at University of Sydney in aerospace. He came to Stanford for both his master's and a PhD. And for most of that time, I've had the pleasure to work with him in my lab. And working with us, not only has he done some just absolutely brilliant work, he's taken our lab in some new directions, but on top of that, especially I think everybody that knows Aditya knows that his personality, he's got a tremendous personality and a wonderful sense of humor. And so all of the meetings we ever have with him are just let's just say they're much more pleasant than I have with a lot of students. So no, it's just been an absolute delight. So let's see, today he's going to be talking about some work that he's done in enabling, I'd say, autonomous robots to explore some incredibly complex and difficult GPS denied terrain. But before I actually turn the floor over to him, just for everybody that hasn't seen one of these before, the format is we're going to have an open meeting here, which is Aditya doing his presentation. That will be followed by an open session where everybody here can ask questions for a while. And then following that, Aditya's committee will take him into the back room and we'll continue the discussions there. But since that, I said that, so what I would request is, and it looks like everybody has already done it, but please stay muted throughout the duration of his presentation. And with that, I think I'm going to turn the floor over to Aditya. So, floor is yours.
Okay, great. So yeah, just to echo what Professor Rock said, please stay muted for the presentation. You can keep your video on if you'd like. What you can do is you can organize your view to minimize and keep that little box in the top right of the screen. And that means you'll be able to see everything that's on the slides. And yeah, I'll be happy to take all your questions by the end of the talk, at the end of the talk. So let me just go into here. Well, thank you, Professor Rock, for the introduction, and good afternoon, everyone. Today, I'll be presenting my PhD research titled Autonomous Exploration of Complex Environments Using Active SLAM. My work is motivated by the need to conduct surveys of complex terrain in remote environments. Now, you can just imagine the scientific discoveries made possible by sending a submersible robot to explore under the ice of Europa, or using the helicopter that landed along with the Ingenuity rover to explore the canyons of Mars. Now, navigating in environments like these presents a challenge because robots here don't have access to accurate navigation systems like GPS, and they have to rely on the terrain itself to navigate. Terrestrial examples of these environments can be found underwater, and these offer insights into diverse ecosystems and unique natural processes that are of great interest to the scientific community. We at the Aerospace Robotics Lab have a unique opportunity to work with the Monterey Bay Aquarium Research Institute, or MBARI, to support these missions. My contribution has been to develop an algorithm to enable a robot to autonomously survey complex terrain like that shown here without reliance on accurate navigation. Survey missions of these sorts of complex terrain build 3D reconstructions of the environment. This reconstruction is available after the survey is complete. But during the mission, survey progress is tracked using 3D coverage maps. These maps show the current status of the mission, and they're made up of little units of volume called voxels. And this coverage map is important because it can identify any regions that were missed without going to the trouble of building an entire reconstruction. Most coverage maps are built by projecting what the robot sees from where it's positioned. Now, here on this slide, you can see some examples of 3D reconstructions versus coverage maps made of voxels. In this left example, the coverage map was built using positioning data from GPS. And in the right example, an accurate underwater localization system was used. Accurate localization is important because coverage accuracy degrades when localization quality is poor. My research is focused on maintaining coverage accuracy when access to accurate localization is not available. And in the process of achieving this, I've used 2D surveys as a stepping stone, and as a result, I've made contributions in 2D surveying as well. So for this talk, I'm going to present my 2D contributions first, and then build on that to talk about the work I've done in 3D. The goal of a 2D survey mission is to build a picture mosaic of the terrain like the one shown here. A 2D coverage map is made of pixels, and it contains information about which parts of the terrain were seen by the camera that's looking down at the ground. In this example, white pixels represent covered and black represents not covered. Coverage maps like this are made by projecting the camera footprint from the trajectory of the robot that's shown here in blue. Now, without accurate localization, this trajectory is susceptible to errors, and the actual coverage map can be different. This discrepancy can cause gaps in the final product, and engineers are then faced with expensive redeployment in order to go back and cover these missed regions. So one step in preventing coverage gaps is to get accurate localization. In many remote environments, like on Mars or underwater, localization methods like GPS are not available. So the simplest method is to localize using odometry. However, this cartoon here shows that due to accumulating errors, the blue true path of the robot drifts away from the red commanded path. And this is because the robot follows the commanded path based on position estimates from inertial sensors only. We can get better performance by using the camera that looks at the terrain to collect additional information in the form of terrain features that are shown here as yellow crosses in the cartoon. This is vision-based SLAM, and it stands for simultaneous localization and mapping. SLAM outputs the position of the robot, its uncertainty, and the positions of features in the environment. These back and forth passes allow the robot to take images of the same stationary features, and these can be used to correct for positioning error. Now, when it comes to underwater surveys, images of the terrain can look like this, and features can be identified across images, as shown here in yellow. Now, the terrain itself can be rich or poor in features. Feature-rich terrain, which is shown here on the left, has patterns that are distinct enough to be recognized in a different photo of the same objects. On the other hand, feature-poor terrain is devoid of these patterns, and it's hard to pinpoint which part of the seafloor this corresponds to. Going back to our cartoon, let's say the terrain is feature-poor. What happens then is that there aren't enough opportunities to see features and adjust the robot's path. This then dictates the need for a more proactive approach called active SLAM. Active SLAM makes the robot go out of its way to intentionally observe what few features are available. The flowchart is changed now to include a path planner that makes the decisions online, so that feature locations are used to minimize the robot's position uncertainty. If there are even fewer features, active SLAM also struggles because there aren't enough opportunities to deviate and reobserve whatever terrain features are available. If we plot the coverage, we can see the result of this discrepancy on the survey progress. the estimated coverage, shown here on the left, doesn't have any gaps, but the true coverage does. This raises two questions. Firstly, if all we can see is the estimated coverage with no gaps, how do we know that there are gaps? We know this because we can infer the likelihood of gaps by looking at the increasing position uncertainty, which indicates that the true and commanded paths are divergent. The second question is, okay, what can we do about it? We can modify the commanded path and compress the space between passes. If done properly, this can close the gaps in the true coverage. This is coverage path planning, and it uses the position of the robot to calculate a coverage estimate. The question then becomes, what does the new commanded path look like so that the gaps in the coverage are minimized? I've addressed this question. I did this by taking this position uncertainty and then feeding it into the mapping box to output a probability of coverage. The effect this has on the cartoon down here is that the estimated coverage becomes blurry when there's likely to be a discrepancy between the true and the commanded paths. This blurred estimate can be used by a new path planner that's designed to maximize the probability of coverage instead of minimizing uncertainty in position. To give a real example, here you can see two coverage maps from the same mission. Using my method, which is calculating coverage with uncertainty, blurs the boundary between covered and not covered pixels whenever the robot is uncertain of its own position. The literature has worked with this idea of coverage path planning, and current active SLAM algorithms plan paths using varying degrees of position uncertainty. Prior work in visual surveying by Galsaran and Kim has used elements of uncertain localization, but pixels were always defined as covered or not covered. There's also been a little bit of work in probabilistic coverage, like that of Yordanova, but not using localization uncertainty. Then a fundamental shift in thinking was applied by Abreu to develop a probability of coverage that varies because of uncertain localization. This method here uses localization uncertainty with a specific sensor model to give probability of coverage. This approach, however, cannot be applied to cameras, which leaves visual surveys in the domain of non-probabilistic coverage. One of my contributions has been to develop a new method for calculating this probability of coverage. My method can be applied to visual surveys, and it's not limited to specific sensor models. I've used this approach in conjunction with a new path planner to enable missions that survey feature-poor terrain in 2 dimensions. Much like 2D, there's been a lot of work in exploring 3D environments. The literature has progressed from the ideal case used by Engler to algorithms that consider some amount of localization uncertainty, usually with a good prior terrain map, like Almadun or Galsaran. Conversely, Schmid doesn't use a prior map, but assumes perfect localization. However, calculating something like probability of coverage hasn't been achieved yet for 3 dimensions. I've filled in this gap in the literature by extending my work from 2D into 3D. As a result, my method builds a coverage map using voxels, each of which has a probability of occupancy. In addition to mapping, I've developed a path planner that enables survey missions in 3-dimensional feature-poor terrain. This change in mindset of maximizing probability of coverage has allowed me to make the following research contributions. I've enabled survey missions in complex 3D environments when the terrain is feature-poor. I did this by developing a path planner to observe frontier regions and a mapping algorithm to calculate a probability of occupancy. I'll cover exactly what all these terms mean a little later on in the talk. In order to enable 3D surveys, I first enabled 2D surveys of feature-poor terrain. This involved developing a path planner to maximize the probability of coverage and a mapping method to calculate this probability. This is the blurring that you saw earlier. I've also made a significant contribution by improving an existing localization algorithm called GraphSlam by making it more robust to errors in feature matching. Unfortunately, in the interest of time, I'm not going to talk about this today, but it'll be in the thesis for all those that are interested. And finally, I've demonstrated these contributions both in simulation and in flight tests on an unmanned aerial vehicle, or UAV. For this talk, I'll be going through the first 2 points, but in reverse. I'll first talk about enabling 2D missions, and then I'll build on these concepts and talk about enabling 3D missions. Throughout the talk, I'll also show how this work was implemented, either in simulation or in flight tests. Bringing these contributions together enables new survey missions. The types of environments that can now be explored include those that have proven difficult for current methods. These environments can exhibit GPS denial, poor visual features, and complex terrain that's not well known a priori. The combination of these contributions is an algorithm that I've called simultaneous localization and mapping, directed by uncertainty-based node connections. This abbreviates to SLAM-DUNC, and it's comprised of the localization, mapping, and the path planning components that I mentioned earlier. So the rest of my talk is divided into 2 sections that roughly align with the contributions I mentioned earlier. In the first section, I'll talk about how 2D survey missions in feature poor terrain are enabled because of my contributions in mapping and planning. And I'll also present some results from simulations and flight tests. Following that, I'll build on these ideas and do the same with 3D survey missions. The key to enabling survey missions in 2D is the path planner, which makes decisions online based on where gaps in coverage are likely to occur, and then drives the robot to cover them. To do that, the planner needs to know the current probability of coverage. So in the first part of this section, I'm going to talk about how this probability is calculated. Then I'll explain how it's used by the path planner. And following that, I'll show you some results from simulations and on a UAV. So just to recap really quick, probability of coverage is what's calculated here on the right. This is the idea that uncertainty in the robot's position causes an uncertainty in what the robot has covered. And I've presented this uncertainty as a blurring of the coverage map. So to understand what this blurring means, let's look at a toy problem. Typically, coverage is calculated by projecting the camera's field of view from the most likely, or the mean position, the mean robot pose. This is illustrated in the figures on this slide. So suppose a camera with a circular field of view is positioned here at 0, 0. But the estimated position is a little bit to the left. The true coverage is a circular footprint centered at the true location that's shown here in purple. Now, if the camera footprint is projected from the mean pose, the result is this coverage estimate on the right. The purple pixels here are correctly identified as covered, but the red area here is false positive coverage, and that's what I want to reduce. This region is wrongly thought of as covered, and it'll end up as a blank spot when the mosaic is generated at the end of the mission. This is generally not a big issue if the robot's well localized, but that can't be guaranteed with vision-based SLAM in feature poor terrain. I've addressed this problem by developing a new method that calculates a probability of coverage. This method accounts for the uncertainty in the position estimate. This uncertainty is combined with the camera field of view to blur the shape of the footprint and calculate a probability of coverage that varies between 0 to 100%. Essentially, the coverage from the camera at a location is weighted by how likely the camera is to be there. Finally, this probability is segmented with a threshold, in this case 90%, which gives the coverage estimate on the bottom right, shown here. Here, the purple and red regions represent the pixels that are at least 90% likely to be covered. And this threshold represents a trade-off, where a stricter limit will reduce the red region as well as the purple region. The mathematical process that calculates the probability of coverage can be explained as a convolution, whereas the original approach just placed the camera's footprint at the most likely position. My method weights the footprint according to the localization probability and integrates over all possible camera positions. Now, one important point to note is that I've made no assumptions about any specific senses or any specific probability distributions. The prior work by Abru that I'd mentioned earlier achieves a similar result, but it cannot be applied to cameras, whereas my method can. The other difference is that my method outputs a single probability of coverage for every pixel, whereas Abru's method outputs a complete probability distribution for every pixel. My convolution-based approach was validated using benthic field data gathered during a survey by Mbari, where the pilots followed a tight lawnmower path and successfully completed the survey. So to better illustrate the benefits of my method, I narrowed the field of view and only took images from alternating passes. The position estimates from a high accuracy navigation system were corrupted with noise, and the trajectory was estimated with GraphSlam. This data was then used to compare coverage estimates using the typical approach and also the method that I've developed. And here are the results. The GraphSlam estimates, so the position estimates, are most accurate in the top left corner where the survey began, and they degrade towards the bottom right of the figure, shown by this discrepancy between the true and the estimated paths. As a result, position uncertainty increases as we move to the bottom right. Now, what you'll notice is if we disregard this uncertainty, the coverage map has well-defined boundaries. But if we incorporate this uncertainty into the coverage estimate, the boundaries get blurrier as the robot becomes more and more unsure of where it is. We can see the effect of this on the coverage estimate by coloring all the false positives in red. As expected, if we ignore the uncertainty, the false positives get worse as the estimated trajectory deviates from the truth. But if we include uncertainty, this effect is greatly reduced. And that's because the effective footprint of the camera shrinks at times of high uncertainty, resulting in comparatively less false positive coverage. In this particular case, false positive coverage was reduced by 46%. And further improvements are possible by adjusting that threshold. But this comes at the expense of true positive coverage. Now that I've explained how the probability of coverage is calculated, let's look at how it can be used to plan a path. Since covering pixels requires taking pictures of the terrain, the planner I've developed places waypoints to serve as imaging locations. These locations are chosen from a list of candidates to maximize a score function. What sets my planner apart from others in the literature is in how this score S is calculated. This is done according to the equation here on the left, and it has two main components. The first part is a trade-off between the new pixels that are covered against the distance traveled. So essentially, covering more pixels increases the score, but traveling further away will reduce it. The second part of the equation calculates whether the expected coverage occurs as a single contiguous block. What this does is that this allows the survey to proceed by incrementally expanding the boundary of the covered region. So let's consider this scenario here on the right, where the robot is surveying a rectangular area. It's traveled along the black line, and it's sitting here at the indicated current position. And it has to decide where to image next. To make this decision, the score has to be computed for every trajectory leading to each candidate waypoint. So one option is to go to candidate A directly and take an image. Another is to backtrack to re-observe this terrain feature here on the right, and then proceed to A. And a third is to move forward to re-image a different terrain feature and then go to A. And the same can be said for candidate B and for C. Now, of all these possible trajectories, the one with the highest score has to be selected. So let's say taking an image after visiting candidate A is expected to cover the purple pixels inside this dotted outline. The same goes for B and C. Of these, the most purple pixels are in A. However, this would create more than one contiguous block of coverage, setting G equals to 1 and score equals to 0. Candidate C maintains the covered area as a single block, but there are no pixels, no purple pixels to give new coverage. So the score of visiting C is also 0. This leaves candidate B as the choice to maximize the score. Now, note that unlike typical cost functions used in active SLAM algorithms, this one does not have an explicit term for path uncertainty, because the focus here is not on getting the best SLAM path, but on maximizing probability of coverage. The uncertainty does come into play, but indirectly, because these new pixels covered already account for position uncertainty from this blurring that happens in the coverage. Now that I've explained how the probability of coverage is calculated and how it can be used to plan a path for the robot to follow, I can show you some results of putting this together. The 2D slam dunk algorithm was demonstrated in simulation and on flight hardware. I'll be presenting results that compare performance in feature-rich and feature-poor terrain for each of these. Simulated missions were done in Gazebo, which is shown here, which is it's an open source physics engine that's widely used for robotics research. The simulated robot was a quadrotor with a downward pointing camera and a corrupted inertial system. The mission was to survey a rectangular area with no prior knowledge of terrain features. This is the result of using slam dunk on feature-rich terrain. Feature richness here is given by the distribution of features throughout the environment. And these features are represented by yellow crosses. Now, the robot starts here from the lower left corner and proceeds, it performs lawnmower-like passes with fairly uniform spacing as it moves up the figure. And there are occasional deviations from this to cover missed spots. The slam performance overall is good because of frequent re-observations of terrain features, and the mission results in complete coverage. This heat map on the right shows the coverage where the pixels here are colored according to the number of times they've been seen. So here you can see all the pixels inside the target area are seen at least once, and repeated observations that are colored more orange and yellow aren't concentrated in any particular region. Running slam dunk on feature-poor terrain has dramatically different results. All the algorithm parameters were kept exactly the same. The only difference between this and the previous experiment is the number and distribution of terrain features, shown again as yellow crosses. In this scenario, the features occur only in the corners and in the center. The robot was initialized again in the lower left corner and started to make parallel passes. However, the lack of feature density led to uncertain localization, which in turn lowered the probability of coverage. The path planner adapted to the situation by narrowing the spacing between adjacent passes. As the survey continued, the planner also frequently revisited terrain features as traveling to a waypoint via informative terrain yielded a better coverage estimate. On the heat map, you can see that the robot observed the center of this target area, the place with terrain features, more than anywhere else. Now, let's see, how would this situation compare to one where we didn't consider probability of coverage? This is how. In this experiment, the terrain was feature poor, but the blurring of the coverage estimate was ignored. Everything else was kept the same. Looking at the path of the robot, there are two things that we can see here. The most obvious difference is this incessant back and forth motion at the top of the figure, which fails to cover the top edge of the terrain. This shows that the planner is aware that something may not be right, but it can't do much more than just re-observe the same region again and again in the hopes that that'll get fixed. Secondly, the parallel passes at the beginning down here don't get compressed. This shows that the planner does not realize that uncertain localization can lead to gaps in the coverage and that a tighter spacing can reduce this from happening. In the end, this mission ends with incomplete coverage. There are about 15 missed spots that are shown here in red, with about 3% of the area being false positives. This is despite making detours to re-observe terrain features like active slam is designed to do. Going back to slam dunk, we can see better performance in feature poor terrain. This is because the path planner drives the robot to maximize probability of coverage. The next step was to take 2D slam dunk to the Boeing flight lab at Stanford University. Flight tests were done on a UAV, which used a downward pointing camera to detect terrain features, just like the simulated one. Here, the features were represented with April tags, which are these unique patterns that look like barcodes. And the robot had no prior knowledge of the tag locations. Positioning was done using a motion capture system, which was corrupted with artificial noise. The mission was to survey a part of the flight room with comparisons made between feature-rich and feature-poor terrain. Here are some sample results from the feature-rich and feature-poor cases. You can see these results bear a lot of similarities to the simulations. The feature-rich mission exhibited paths that were somewhat parallel with detours to cover missed spots, and the feature-poor trajectory was more erratic and displayed passes that were more compressed. In summary, slam dunk performed better than the active slam that didn't consider coverage uncertainty. Firstly, we can see that ignoring uncertainty in the coverage, so not having these blurry boundaries, generates false positives in feature poor terrain. This happens both in simulation and in flight tests. With slam dunk in simulation, coverage is 100% complete for both feature rich and feature poor terrain. And it's close to 100% complete in flight tests, again for feature rich and feature poor terrain. And this is because the planner adapts by reducing track spacing when needed and revisiting observed features to maximize the probability of coverage. The trade-off of doing this is that more feature revisits and a tighter spacing causes the robot to travel more when features are few and far between. This concludes this first section of the talk. I've shown you how I've enabled 2D survey missions in feature poor terrain by calculating a probability of coverage and using it in a path planner that adapts to the condition of the terrain. Now I can build on these ideas to enable 3D survey missions in feature poor terrain. Slightly different to the 2D case, the decision-making process is done by a path planner that reads in a probability of occupancy, not coverage, and observes these things called frontiers to explore new terrain. These frontiers are in turn calculated using a mapping algorithm that also draws on elements from the 2D coverage mapping that I've talked about. In the first part of this section, I'll talk about how this occupancy is calculated, what a frontier is, and then I'll explain how these elements are used by the path planner. And then following that, I'll show you some results from simulations and flight tests. In order to explore 3D environments, we must first define how a 3D map is represented. As I mentioned back in the introduction, occupancy estimation, which is done with voxels in 3D, is slightly more complex than coverage estimation with pixels in 2D. Voxels that have not been observed are thought of as unknown, and observed voxels must be further classified as occupied or empty. So an occupied voxel causes an occlusion, whereas an empty voxel allows us to see what's behind it. To understand how this classification comes about, let's look at this simplified depth camera model that projects light beams out of the camera's field of view. If the beam hits the terrain and then reflects back, we can conclude that the voxel where it happened must be occupied, and that every voxel leading up to it has to be empty. Any voxels beyond the occupied one remain unknown. The next thing we can notice is that further exploration immediately ahead of the camera is not possible. There are occupied voxels in the way that block us from seeing the voxels behind it. What we can do instead is explore to either side. The robot can travel through this blue empty space and potentially see new terrain along this boundary of empty and unknown voxels. This boundary, colored here in green, is called the frontier. And it's a common concept used in the literature to signify the potential for further exploration. And there are many algorithms that explore new terrain by planning paths to see these frontier voxels. Once observed, the frontier voxels themselves become either occupied or empty, and the frontier itself gets pushed further back. Complete coverage means that there are no more frontiers remaining, and that there's no more potential for further exploration. Now, let's see how these frontiers are calculated. Just like the 2D case, let's look at a toy problem. Consider a robot sitting here at 0, 0, observing a wall 1 meter to the right. If we project beams of light from the field of view, we can mark the voxels containing the wall as occupied and the voxels leading up to it as empty. The voxels in this center figure here are colored such that blue is more likely to be empty, red is more likely to be occupied, and green is unknown. We can also display only the frontiers, shown here on the right figure. So here you can see that there's no potential for exploration immediately to the right of the robot because there's a wall there, but we can explore to either side of it. This is the ideal case. In reality, the estimated position can have an error that's given by a position and uncertainty that's typically ignored. Using the same approach as before, we get this occupancy map. Now here, the true wall is overlaid to show that this position error causes the voxels that make up the wall to be thought of as empty, and this increases the chances of a collision. The other point to consider is frontier voxels. The frontier voxels represent the potential for further exploration, and the ones shown here suggest that there's no potential for exploration to the right side. So not only is the wall detected incorrectly, but the map suggests that there's nothing more to learn from this region. So let's move these figures up and see what I've done to address this issue. Much like the 2D case, my approach considers the robot's position uncertainty. The resulting occupancy map is blurred according to this uncertainty, and it has two key effects in this example. Firstly, the walls that make up this wall no longer appear as completely empty. And secondly, if we look at the frontier voxels, my approach suggests that there are voxels to the right that require further investigation, and that the shape of this region matches that of the wall. So you can see that with my estimation approach, a potential for error is recognized, and the shape of the obstacle still comes through. This new occupancy mapping method was developed by modifying an existing approach. The original method, developed by Clemens, represents the occupancy of each voxel as a beta probability distribution, which in turn is defined by two shape parameters, alpha and beta. These parameters can be thought of as a tally of how many times the voxel was observed as occupied or empty. So if you think the voxel is occupied, increase alpha. If you think it's empty, increase beta. This method generally works well, but it has limitations when the robot position is uncertain. And you can see that there's no term for position uncertainty in these parameter update equations. My contribution was to modify these equations to incorporate robot position uncertainty, as shown down here. The math is different, but the concept is the same as the 2D case. The magnitude of the update is weighted by how likely the robot is to cause such an update. The end result is a smearing of this parameter update to include nearby voxels, and that depends on the uncertainty of the robot's position. Now that I've shown you a way of calculating this probability of occupancy and picking out frontiers, we can develop a path planner that makes decisions and drives the robot to observe these frontiers and explore new terrain. Path planners that explore in this manner by pushing back these frontiers are called frontier-based methods. The key to this approach is to evaluate how many frontiers can be seen from a number of specific viewpoints or nodes, and then the decision can be made that favors the node with the most visible frontiers. Now, what most frontier-based methods do is just count the number of frontiers in the robot's expected field of view. But in reality, the expected position of the robot is uncertain, and it has a probability distribution. The planner I've developed samples this distribution and calculates a likelihood of frontier observation. Now, the decision to favor one path over another is based on maximizing the probability of frontier observation. This approach ties in the localization uncertainty to the exploration of new terrain. So what this means is that if there are lots of frontier voxels, precision is not necessary. But if a specific voxel needs to be observed, it has to be done accurately. I've incorporated this approach into a well-known path planning framework called fast marching trees, or FMT style. FMT style works by building a tree of possible trajectories evaluated according to a cost function, and the trajectory with the cheapest cost is selected. The FMT star framework has several advantages compared to other popular algorithms, and that's because it expands this tree in a very cost-effective way, and it also saves time by performing some calculations in parallel. The most important component of the FMT star is the selection of an appropriate cost function. This is the equation that determines which path to take. Now, because surveying unknown 3D environments is a complex process, I've developed 3 separate cost functions. These are tailored to the kinds of behavior that I want the robot to embody at different stages of the mission. Which cost function to use is selected by a state machine, and that follows this flowchart shown on this slide. The mission starts with the robot having a greedy strategy. At this stage, not much of the environment has been explored, so I want the robot to try and observe as much as it can in its immediate vicinity. Once enough of the environment has been seen, the cost function shifts to a targeted strategy. At this stage, there are smaller pockets of unknown space remaining, and the robot tries to observe these even if they're far away. The last strategy is activated if the robot position becomes too uncertain. In this case, it'll stop looking for frontiers altogether and try and re-observe terrain features instead. To better explain this behavior, I'm going to take you through an example of each strategy. This is the greedy strategy. The figure on the left shows the terrain observed so far and the path taken during the greedy planning phase. On the right here is the tree of possible paths. The robot starts at the red dot and then ends the green dot. What you can see is the tree isn't very extensive, and that's because the robot is only interested in the local vicinity, but it wants to see as much of the environment as it can. So this is done, you can see here, by having a lot of heading changes. The robot almost rotates on the spot. The cost function in this case is a balance between frontier likelihood penalized by the amount of distance traveled. Here is an example of the targeted strategy in action. The figure on the left here shows the frontier voxels that need to be covered as green and blue cubes. The robot starts the red dot and takes a direct path to this cluster here on the left, where it tries to observe the cluster from a variety of viewpoints. The underlying tree of possible trajectories that governs this behavior is shown here on the right, colored according to the cost of travel. You can see that the cost increases as the robot travels further from the start location, but then decreases sharply when the tree reaches the frontier cluster. The cost function that governs this behavior is related to the number of frontiers observed, but there's only a very slight penalty for distance traveled. And finally, the localization strategy is purely for re-observing terrain features and reducing the uncertainty of the robot's position. The cost function is very simply a measure of the robot's uncertainty, and the tree expands radially out from the start location. Now that I've covered how the map is made and how it's used by the planner to cover frontiers, I'd like to talk about implementing 3D slam dunk on a UAV. This was done in simulation and also in flight tests. Simulated missions were done in Gazebo, and flight tests were performed at the Boeing Flight Lab at Stanford University. In both cases, the robot was a quadrotor with a forward-facing infrared depth camera. Localization was done similar to the 2D case, with a corrupted inertial system and a downward pointing camera that detected April tags. Now, if you remember, these tags look like barcodes and work as a stand-in for image features. The robot was tasked with surveying a rectangular volume with no prior knowledge of April tag locations. The shape of the simulated terrain is shown here on the left. The terrain took the form of this L-shaped canyon with nearly vertical walls. There was also an archway that spanned across the canyon with a clearance large enough for the robot to pass underneath. Now, the first step in the survey is to do a pass at a safe altitude, with the sensors pointing downwards to generate a rough prior map, like the one shown here on the right. And this is common for current survey methods. Now, slam dunk doesn't explicitly require a prior map, but it benefits from having more information before proceeding to a closer inspection of the terrain. Many of the underwater sites that we'd like to survey already have rough prior maps available from earlier missions. These missions were carried out by autonomous robots flying at a safe altitude using sonar sensors. So the maps generated have a lower resolution from the altitude and don't contain visual features because of the lack of a camera. Additionally, because these maps are generated from the top looking down, the terrain isn't represented in its full complexity. For example, the sensors can't see under any overhangs, and the arch over the canyon just looks like a large solid obstacle. So like I said, a prior map is not necessary, but slam dunk benefits from having this additional information. Keeping in mind that the map is not completely accurate, it's used in the following way. everything above the map surface is thought of as empty space, and everything below it is made of unknown voxels. Being on this boundary between empty and unknown, the prior map surface gets turned into frontier voxels, which are ripe for exploration. Now, this is what the simulation looks like when the terrain is feature rich. As you can see here, features represented by orange crosses are distributed throughout the map. Surveying this terrain using slam dunk gives the map estimate here on the right. What you can see is that the estimated terrain looks very much like the truth. There's a plateau here on the left, the L-shaped canyon, and the archway that spans across it. Many of the features are detected and their positions are estimated here as well. The accuracy of slam dunk can be measured by how well this estimated surface matches the true surface. And I've evaluated this performance using a metric called boundary closeness, which is a measure of how well the estimated terrain conforms to the truth. Now, because this is a distance between the true and the estimated terrain, smaller numbers are better. For the feature-rich case, this value on average is well below the side length of a voxel. State-of-the-art algorithms in the literature perform along similar lines, estimating terrain well within one voxel. However, this performance is very closely tied to the accuracy of whatever localization algorithm is used, which inevitably degrades in feature-poor terrain. The key contribution of slam dunk is to maintain good performance in feature-poor terrain. This is done by disconnecting mapping and localization performance. So to test this, the simulated terrain was changed to have image features here only on the plateau in one corner, and the rest of the terrain contained no image features at all. Surveying this terrain using slam dunk gave the map estimate shown here on the right. By inspection, you can see that the estimated terrain looks a lot like the simulated one. Now, this is despite the lack of image features in most of the environment. Looking at the metric in the table below, it's evident that slam dunk performs just as well in feature-poor terrain. The average value is well within one voxel size, and the maximum value was about 0.5 meter, which is within the obstacle avoidance limits for the path planner. This performance is achieved because the robot makes repeated excursions to re-observe terrain features and then closes gaps by maximizing the observation of frontiers. This is why, similar to the 2D case, the total distance traveled is higher for feature-poor terrain. Slam dunk in action is better understood when seen in an animation. This is the simulated robot surveying feature-poor terrain. The robot starts off in the flat region and then makes its way out into the canyon. The voxels here are colored to represent increasing likelihood of occupancy from yellow to orange to red. You can also see that the robot makes frequent revisits to the feature-rich plateau, and this serves to increase the likelihood of voxel observation in other parts of the map. The previously unmapped archway is identified correctly, and the robot can actually pass underneath it without collision. This mission here ends with complete coverage, meaning that there are no more frontiers left to be seen. Now, this animation helps humans understand what's going on, but other than to avoid collisions, slam dunk isn't concerned with occupied voxels too much. The focus of slam dunk is actually to maximize coverage, which in 3D means to maximize frontier observation. This animation shows the same mission as before, but it plots frontier voxels. The prior map comes into play and sets the initial landscape of frontier voxels. The robot proceeds just like the previous animation, but here you can think of it as vacuuming up frontier voxels. Additionally, the voxels here are colored such that the yellow ones are likely to be occupied and blue are likely to be empty. I've also plotted the terrain features here as yellow crosses, so you can see that they get detected. You can see that the robot makes these repeated returns to observe these features, and that reduces the number of frontiers in the rest of the map. And the end result is a map with no reachable frontiers remaining. Slam dunk was also demonstrated in flight tests on a UAV. The terrain was constructed using cardboard boxes, and the features were represented with these April tag printouts glued onto ceramic tiles. The locations of these boxes were used in a rough prior map, and tag locations were completely unknown a priori. The UAV was an Intel Aero drone that was purchased off the shelf, and it came equipped with a forward-pointing infrared depth camera, which was used for the occupancy mapping, and a downward-pointing vision camera that was used to detect the April tags. Like the 2D flight tests, positioning was done using a motion capture system, which was corrupted with artificial noise. The terrain contained simple elements like short obstacles, a vertical spire, and an archway that was large enough for the UAV to fly through. The prior map, shown here on the right, served as a rough guide to aid the algorithm in the simulated missions. Once again, the archway was modeled as a large solid obstacle in the prior. This video here shows the UAV in flight, and the estimated terrain is shown here in the lower left corner inset. The mission began with no occupied voxels estimated, and it ends with a complete map of the terrain. You can even see shortly that the UAV will pass underneath this archway that was previously unmapped. This table summarizes the performance of Slam Dunk, both in simulation as well as flight tests. Comparisons here are made in terms of two metrics. The first is boundary closeness, which, as I previously mentioned, is a measure of accuracy. The other is voxel incursion, which measures the incursion of estimated terrain inside the true terrain. Again, smaller numbers are better because this reduces the likelihood that an obstacle is closer to the robot than expected. The two metrics essentially gauge accuracy and conservativeness. The simulation numbers are the same from a few slides ago and show similar performance in feature-rich and feature-poor terrain. The flight tests tell a slightly different story. Here, the map is slightly less accurate in the feature-poor case, but just as conservative. This means that in the event of a less accurate map, Slam Dunk doesn't compromise on conservativeness. This behavior is desirable because when flying with poor localization, it's safer to estimate obstacles as being on the larger side. And just like before, the feature poor case causes the robot to cover more distance as it revisits features to maximize coverage. In conclusion, Slam Dunk enables new survey missions. It gives robots the ability to explore remote, hazardous environments in the absence of GPS. It produces accurate maps even when the terrain is poor in visual features, and if the accuracy degrades, it maintains conservativeness. Slam Dunk does have some limitations. For example, the cost functions that I've used for the FMT star path planner don't satisfy the triangle inequality, which means that many of the optimality guarantees of FMT star cannot be applied. Additionally, constraints on the sensor field of view and the lack of an upper bound on the position uncertainty means that complete coverage can't be mathematically guaranteed. Despite this, Slam Dunk exhibits good performance in feature-rich as well as feature-poor environments, and that's something that other algorithms have struggled to achieve. In the process of developing Slam Dunk, I've made several research contributions. I've developed path planners to maximize frontier observation in 3D and probability of coverage in 2D. I've developed mapping algorithms to calculate probabilities of occupancy and coverage using position uncertainty. I've also improved the robustness of GraphSlam to false feature matches, something that I didn't have time to talk about today. And finally, I've demonstrated this new capability of autonomously surveying feature-poor terrain, both in simulation and on robot hardware. Slam Dunk has plenty of potential for improvement. Avenues for future work lie in each of the core components. In localization, GraphSlam is an efficient way to solve the problem, but it's limited to Gaussian probability models. Using a non-parametric filter would be one way of addressing more complex models of uncertainty. With regards to mapping, occupancy grids are very common and intuitive. However, this comes at the expense of computation and memory, especially at high resolutions. So refactoring the convolution approach for octrees or Bayesian-Hilbert maps would greatly improve the efficiency of slam dunk, and it would enable exploration of much larger environments. In terms of planning, both the 2D and 3D planners I've developed can search multiple paths in parallel, but each path calculation remains quite slow. Additionally, the cost functions I've used don't satisfy the conditions needed to guarantee optimality. So further investigation in this area is also needed. And finally, slam dunk needs to be demonstrated on an underwater vehicle in the deep ocean. This is something that would be really cool to see. Pursuing this line of research would bring many challenges in the form of control actuation and potentially avoiding moving obstacles like fish. It's my hope that my work here forms one brick in the wall towards building a fully self-contained and optimized active SLAM exploration system. And with that, I'd like to conclude my presentation. But before I take your questions, I want to thank the people that have helped and supported me on this journey. But before I get to that, I'd like to tell you about a tradition we have in the lab, where every time we present at a meeting, we get to talk about a topic that has nothing to do with our research. And it's a bit of fun, and the only requirement is that the title of the topic abbreviate to PhD. So I'd like to do my acknowledgements as PhDs. Firstly, I'd like to thank the Monterey Bay Aquarium Research Institute for their support. MBARI is filled with a lot of brilliant engineers who love robots and the science that they enable. I've had the opportunity to get out on a boat and watch MBARI operations, and it was a very cool experience. I'd like to thank my committee for being here today and for their guidance and advice over the years. Professor Rock, thank you so much for giving me ownership of my research. It's made this PhD a very educational experience. Professors Kokendorfer and Schwager, I'd like to thank you both for being approachable and ever ready to answer my questions. Professor Alonso, thank you for joining me today, and thank you for being a friendly face in the department. And finally, Professor Kenny, thank you for chairing this defense. Intro to Mechatronics was probably the single best class I've ever taken. Building those robots for that basketball challenge was an incredibly enjoyable and a very rewarding experience. I'd also like to thank the AeroAstro staff for constantly making sure all my paperwork and all my reimbursements and all the forms I had to fill were all in order. So thank you. I'd like to thank my friends from here and from abroad. Your support and your friendship has really meant a lot over the years. And it's a little suspicious that the year I got the most work done was the year I wasn't allowed to spend time with any of you. But I'm looking forward to hanging out as soon as it's safe to do so. I'd like to thank my family, spread across 5 time zones, each split 4 to 6 hours apart. So I know it's impossible to have everyone awake at the same time. So thank you for waking up early or staying up late. I want to also thank my family on the Dustin side, collectively called FamJam. I'm very fortunate to have such a close-knit, extended family, despite the physical distances between us. I'd like to thank my parents, who woke up early to watch this from Australia. Without them, I wouldn't be where I am today. Thank you for raising me with love, kindness, and teaching me to appreciate the value of education. I'd like to thank my sister for being an awesome friend and being supportive whenever I was feeling down by absolutely destroying me in online video games. And last but not least, I'd like to thank my lovely wife, Megan. One of the things we both love to do is travel, and Megan made the mistake of planning our first vacation and doing a great job of it. So now she's stuck with that job forever. In the few years that we've been married, we've had the incredible good fortune of visiting every continent except South America, which we're going to get to as soon as it's safe. She loves planning trips so much that I've actually set a rule of no planning vacations until the current one is over. Megan, your love and support have meant so much to me, and I'm looking forward to more travel, fun, and excitement in our future. And with that, I'd like to thank you all for joining me today, and I'm open to taking any questions.